a large weight, on the regression coefficients. And in calculations, it is going to have an improportionate impact. It's not good. Also, I should mention that we do not want to predict the unusual data points. So later on, we want to use this model to predict the typical data points, the common data points. We cannot predict the unusual data points anyway. So why would we fit our model to unusual data points? We shouldn't do that. We should fit our model to the common data points, such that the results, the estimated model, can be used to predict common data points. All right. We are going to talk about the taxi data set. For example, it has several outliers. I ask you to just load the taxi data set, taxi CSV. While you're reading the data set, I'm going to just explain how to handle the outliers, and after that, we're going to just do the methods together. Use the methods together. The first option for handling outliers is ignoring outliers, like what we did so far, like what we have been doing so far. We just ignore the outliers and assume that we don't have any outlier. We just use all the data points in the data set. The other option is to trim the outliers. Trim means just excluding the data points that are just considered outliers. To do that, we can use IQR or percentile to detect the outliers. There are different methods to detect outliers. We can use percentile, that means just the top 1% and the bottom 1% of the data are considered outliers. Or we can use IQR, which is a slightly more complicated technique. I'm going to explain in a bit. The other method to detect outliers is just visual inspection. Just visually inspect and find the outliers. There are other methods too, but just keep these three methods in mind. After we detect the outliers, we should decide what to do with them. One method was trimming. The other method is winterizing. Winterizing means moving the outliers towards or into the acceptable boundaries, acceptable region. Instead of just excluding them, we just move them around. That is helpful when we don't have many data points and we want to use as many data points as we have to estimate the coefficients. Okay. Let's see an example. First of all, if we want to ignore the outliers, we can just ignore them. It's going to reduce our predictive power and our generalizability because our model is fitted, is customized to the outliers. The other method is trimming. We specify the upper bound and the lower bound somehow, and then we exclude the data points that are beyond these bounds, these boundaries, like this. Exclude the data points. To find the upper bound and the lower bound, we have two methods. We have actually three methods, two systematic methods. Percentile would be just top 1% and bottom 1%. That's very straightforward. And IQR is based on this formula. Lower bound would be Q1 minus 1.5 times IQR. and the upper bound would be Q3 plus 1.5 times IQR. And what is IQR? IQR is this, Q3 minus Q1. What are Qs? They're quartiles. So the first 25% is Q1, second 25% is Q2, third 25% is Q3. So actually, first 25% is Q1, then 50% Q2, 75% is Q2, right? So the difference between Q1 and Q3 would be called IQR. IQR is the difference between QR and Q3. All right. Now, the upper bound would be Q3 plus 1.5 times IQR, and the lower bound is Q1 minus 1.5 times IQR. Why would we use IQR instead of percentile? That's because if we use percentile, what happens is that sometimes the data are very skewed, that a large portion of data is in the top 1% or in the bottom 1%. So we have, like, let's say that the distribution of data are like this. So we have data points here, and then we have a lot of data points in the top 1%. So if we exclude the top 1%, we are excluding like half of the data. That's not good. In these situations, we better use IQR. When the data is not distributed normally or uniformly or just something reasonable. But if data is very skewed, in those cases, we better use IQR, because obviously these data points are not outliers. You cannot have this half of our data. You cannot just label half of our data as outliers. It's not good. Therefore, we have 3 methods. In total, we have 3 methods to detect outliers: IQR, percentile, and visual inspection. I didn't include visual inspection here because it is not a systematic method, and I'm not going to ask questions about them in the exam or the homeworks. So there are methods to detect the outliers, and there are methods to handle the outliers. After detecting the outliers, after specifying the upper bound and lower bound, then what should we do with them? What should we do with the outlier? One approach was to trim, just exclude them. The other approach is to winterize, move them and put them inside the boundaries. And again, you can just use the IQR method or the percentage method, percentile method to detect the outliers or to identify the outliers. Okay. In general, we have like 5 methods. In total, there are 5 methods. 1 is ignore. 2 is trimming with percentile. 3 is winterizing with percentile. 4 is trimming with IQR. 4 is winterizing with IQR. 5 is winterizing with IQR. There is also a 6th method. There is also a 6th method that I should mention. And the 6th method is adding a new variable to your model to separate the outliers from the rest of the model. In that case, we don't call them outliers anymore. Just that variable is like the categorical variable. That categorical variable can just separate the outliers from the rest of the data. If there is a specific characteristic for the outliers, that characteristic can be used as a variable, as a categorical variable, usually binary variable. So what method is the best? Ignoring, trimming, winterizing, trimming with percentile, trimming with IQR, winterizing with percentile, winterizing with IQR. Which one is the best? First, we should use our intuition and reasoning. Secondly, we should use the accuracy on the test set. The accuracy on the test set is very important. If we want to use our model for explaining variation and interpretation of the coefficients, then R squared is also good. We can decide based on R squared. But if we want to use our model to make predictions, in that case, the accuracy of the model on the test set is more important. Okay, and we can compare the accuracies of these methods on the test set and see which one performs better. All right. Now let's go to R and do the coding together. I'm gonna just open the script. You can download this script from Canvas, outliers.r. It is in module Advanced Topics. Change your working directory, and access the course data. Now, of course, first you should read the file, taxi.csv. It is a large file, but 500,000 data points, 500,000 trips, they're trips. And I'm not gonna make the scatter plots yet because it's a large data set and it takes a long time to make the scatter plots. How many data points do we have? Length of one of the columns would be the number of observations. In this case, we want to estimate the relationship between fair and distance. Particularly, fair is the dependent variable as a function of distance as the independent variable. And the number of data points are 453,197 trips. What is the first step? Remember, we want to cross-validate. We want to calculate and estimate the accuracy of the model on the test set. What is the first step in dealing with this data set? What is our first step in cross-validation? Split the data. Split the data into training and test, right? Split the data. Okay. Taxi.csv is a bunch of trips. Is it a time series or not? Is it a time series? It's not a time series. It's just a bunch of trips, right? That means, how should we split the data? How should we find the training set? Go ahead. Randomly, exactly. So we should randomly select 70% of the data and use them for training. So we should use sample of 1 to n, 70% of the data, and put that in training set, in training, and the rest would be used for test. 30% of the data. We use those indices to just extract the training set and put that in the train, and extract the test set and put that into test. So we have our training set and the test set. The first method is ignoring. Just estimate the model as usual. I'm gonna just do this. Oh, by the way, I want to plot the data so I see if I can detect some abnormalities before using the methods. before using any method, I want to just plot the training set. I want to plot the training set because the outliers in the training set are the outliers that matter. We don't care about the outliers in the test set. The outliers in the training set are the ones that matter. Why? Because we use the training set to estimate the coefficients. And the outliers, if we have outliers there, those outliers can just bias our estimates, right? So we want to see the scatter plot on the training set. However, in this case, our training set is very large. I'm gonna just use the test set to see the scatter plot, but normally we should just look at the scatter plot in the training set. Of course, they should be very similar because it's randomly selected. They should be very similar, except the test set has fewer observations. Cannot show even the test set. Okay. Oh, show the test set. Let's look at the scatter plot and see what we have. Just let's analyze the scatter plot and visually inspect the scatter plot and see if we can detect the outliers. I think this data point is an outlier. Also this data point and this data point. All these data points are outliers. You know why? No fare. The taxi driver did not charge the passenger. We have distances, but no fare. Here, we have no distance, but some fare. Probably it was waiting time or canceled trips, right? This one, it's a small distance. It's a short distance, but a large fare, more than $200. Something is going on here. What other outliers can you detect here? Can you point out any irregularity in this scatter plot? Anything unusual? Sure. 250 here.
Yeah, both of them.
But what? This one?
No, all the way on the left.
You mean this one?
Yeah.
Yeah. So this is an outlier, definitely. Anything else? Do you notice? Okay, go ahead. 450. This line. So yes, you are right. It's unusual. You have a line of observations here. Something is going on here. It is not normal. We normally expect that when we have a longer distance, we should see a larger fare. But this line here, there should be an explanation for this line. And there is actually. It happens that there is an ordinance in the New York City that every trip from the airport should have a fare of $50. There is a fixed fare for the trips from the airport, apparently. And these trips are from the airport. And that means there is something that is explaining this abnormality, right? So what's your name? Kelsey. You get a bonus. Now that we analyze the data, let's go to the code. Let's see how we can code everything. Yeah. When we ignore, we can just estimate the coefficients like this as before. It's very straightforward. And the result would be both coefficients, the intercept and the slope, are significant. The R squared is 87.5%. So 87%, 87.5. That's R squared when we ignore the outliers. Now, let's use the trimming with IQR. Trimming with IQR 4. This is number 4. Actually, I think we better use trimming with percentile first, then we go to trimming with IQR. This would make more sense, right? 2A, 2. So trimming with percentile, it's very straightforward. 99%, 1%, top 1% and bottom 1%. We get them and put them in Q. Use quantile function to get the percentiles. Lower bound would be Q1, the 1%, and upper bound would be Q of 2, 99%. Q stands for quantile. And now we want to get the part of the data that lies between the upper bound and the lower bound. We use which of fair more than lower bound and fair less than the upper bound. When we use which of that, it gives us the positions of the observations that are not outliers. The train of that would give us those observations. Therefore, U is the cleaned training set. We use U instead of the train. U $ fair as a function of U $ distance. And summary, the result would be this. So this is the result of the trimming with percentile. R squared is 88.45. 88.45. The other one, original one was 87.48. So trimming with percentile, 88 point, how much? Percentile, 88.45. What 1% higher? Okay, 1% better. That's fine. Now let's use IQR to specify the lower bound and the upper bound, and then trim. First, we can use quantile to specify Q1, Q2, and Q3. 25%, 50%, and 75%. And Q1 minus 1.5 times Q3 minus Q1 would be the lower bound, and Q3 plus 1.5 times Q3 minus Q1 would be the upper bound. Q3 minus Q1 is IQR. We call that IQR. I should mention that we really don't want the 50%. We really don't need the 50%. So what we can do is that we can just say quantile 25% and 75%. 25% is Q1, 75% is Q3, right? And here we are going to say Q of 1 minus 1.5 times Q2 minus Q1. Why am I saying Q2? Here, I'm not saying Q3. I'm saying Q2 here. Q2 minus Q1. Because the second Q is actually Q3. The second Q is 75%, which is Q3. So Q of 2 is actually Q3, right? The second Q is Q3. So it is Q3 minus Q1 actually. And this way we can just find the lower bound and the upper bound. We already found them. So they're equivalent. Then what we do is that the rest is like before, like percentile. We just extract that part of the training set that satisfies this two conditions, fair more than lower bound and fair less than upper bound. That specifies the part of the data set, the part of the training set that satisfies these conditions. We have this, and they excluded the outliers, they included the others. So technically, actually, probably better put equals as well. So, because actually here we don't need to put equals, but here, if we put equal, makes more sense. So we want to include the upper bound and the lower bound also in our analysis. And after that, you have a new lower bound and new upper bound. T, so T is the part of the training data set that we are going to use, the trimmed part, trimmed using the IQR method. Bit 2 is the result. Let's see what we have. Both of the coefficients are significant. The intercept and the slope are significant. R squared is much lower. It's 77. 7.8. So R squared is lower when we use IQR. So far, trimming with percentile wins. Let's see what other method we have. We can use Winsorizing. And to Windsorize, let's Windsorize using percentiles. We specify the percentiles as before. We probably don't need to repeat it because it is the same upper bound and lower bound as we had for trimming for percentile. And this time, instead of excluding the outliers, what we do is that we reassign new values to the outliers. So wherever the fair is less than the upper bound, we assign the value of the less than the lower bound, we assign the value of the lower bound to the fair. Right? And whenever the fair is more than the upper bound, we assign the value of the upper bound to the fair. We are just manipulating the data. So now we don't have any outliers because we moved the outliers into the boundaries that are acceptable. We run the model again with the new data set, with the new data that we have. You have the same number of data points now. You have the same number of data points. We did not exclude any data points. With this new one, R squared is 88%, 0.6. So a little bit more than 88%. So 88%, 0.6. Now, I want you to do something. To do the last part. Windsorize using IQR. So it is method 3A. I want you to do method 3B. Windsorize using IQR. As a hint, you can just copy and paste most of the code from before. So it is 3B. Method 3B. To specify the Q's, what should you do? You should use IQR, not percentile, right? Just like here. We have the code here. You just grab this code from here to B and put it here instead of the percentile method. Right? And you have the upper bound and the lower bound as before. But instead of excluding the outliers, we are going to be assigned the upper bound and lower bound that we found using the IQR. And that's it. We have the new one, the fit 5. So fit 4, oh, actually 3 and 4, yeah. So this would be the new code. Let's run them and see what happens. We're gonna just run the regression, and the result is not good actually. When you use IQR and winsorizing, the result is not good. R squared with that, IQR winsorizing. R squared with that, let me run it again to make sure, is 69%. 69, actually 69.1. This is based on the R squared values, which method is better? Ignore, trim percentile, trim IQR, winsorize percentile, winsorize IQR. Which one is better? Winsorize percentile and trim percentile, both of them are good. So using the percentile is better than IQR apparently. Go ahead.
What are you looking for it to do the best?
The R squared values. Higher R squared values are better.
So are you just saying it's closest to ignore?
No. Ignore is 87%.
Oh, it's 87.
We are trying to
I
top
thought
that.
I thought it was 89.
No. Oh, so we are trying to top that.
The highest percent.
The higher the better. But of course, if our goal is what? Interpreting the coefficients and explaining variation. But what if our goal is something else? What if our goal is predicting the future? In that case, you have to cross-validate. And you have to compare the accuracy of the model on the test set. Meanwhile, I should mention that if we run everything again, we will get different R squared values. You know why? Random sampling. Each time that we split the data, we're going to get a different training set. Okay? And the results will be slightly different. But generally, we can tell that percentile is better than IQR in this case. And most likely percentile is better than IQR. So we should use percentile. And between trimming and winsorizing, I would use trimming in this case because we have a lot of data. the taxi driver has the taxi data set has a lot of data. We are not short of data. Okay. Now we want to I want to calculate the accuracy of the model on the test set. Accuracy of different models on the test set. First, we have the values of the independent variable on the test set. It's here. We test distance. Distance is the predictor on the test set. We get it from the test set. X is from the test set. The actual values for the dependent variable also are in the test set. Test actual, the dependent variable, fair. We want to calculate the predicted values for the dependent variable, y hat. So this is why we want to calculate the y hats on the test set. How do we do that? We have the x, of course, and we have the coefficients for from each model. Each model gave us different coefficients. Use the coefficients on the x's from the test set. We obtain the coefficients from the training set. And we calculate the y hats for the test set, like this. And now that we have y hats, y minus y hat would be the residual or the error. The error. So the errors that we get for the test set, when we use the first model, the first method, ignoring, would be this. Test residue 1. That's the list of errors, the vector of errors. All of these are vectors, by the way, are lists. The same is with the second method. Actually, the second method would be trim. Trim 1% on each side. Yeah. The second method, trim 1%. This is the second. The coefficients fit 2. Second method. Let me see if I have put everything correctly. So this is ignore fit 1. Oh, fit 2 is this. Yeah. So I'm gonna just rerun everything to get the correct values. And fit 3 is this one with IQR. Fit 3 is with IQR. So I'm gonna run everything. Get that, and fit 4 is right. So we have fit 2 y hats using the coefficients obtained from the second method, y hats using the coefficients obtained from the third method, IQ1 trimming, and y hats using the coefficients from the fourth method, means rising using percentile, and there is also one more. The last one is this. Coefficients that we obtained from means rising using IQR. Means rising using IQR gave us these coefficients, fit 5, and the coefficients that obtained, x stays the same. The independent variable, the values of the independent variable are from the test set, and the test and the residuals are calculated like this. So as before, the actual values, similar everywhere, minus the predicted values from the using the model, the last model. So we have that. So now we have the errors from each model, each of the 5 methods. We have 5 sets of errors, 5 sets of residuals on the test set. For the accuracy, how can we measure accuracy? or the predictive power, abs mean or average of the absolute values of the errors. Mean of abs of errors. So mean of abs of errors for the first one is this, the second one is this, third, fourth, and fifth. Mean of the absolute errors. Something is right here. Longer object, shorter object here. Okay, go ahead. What's up?
I got it. I got two.
You got 2 for all of them?
Yeah, I think mine's right.
Or maybe mine's are not good. So why there are 17 something? Just crazy. 1, 2, 3, 4, 5 values. Possibly that I calculated something. So what we can do is that we can run everything. Again, let's see what happens. So we should compare the values, and so as you can see, I selected all the code and I'm running all the code. The reason it has some delay. It has some delay because of the plot, the scatter plot takes long time. Okay, we should compare the values of these average absolute values for the residuals, and which one is the best? The lowest one or the largest one? The smallest one or the largest one? The largest? The largest one is the best. The largest errors is the best. No. The smaller one. The smallest one would be the best. And yeah, so you are right. There should be 2 something. I don't know. Something was off there. I got 1 number. But for the first method, which is actually the ignoring method, you get 2.063. Then you have 2.069, 2.04, 2.09, 3.4. So 3.4, yeah, that makes sense. When in Windsorizing, so this is the 5th one. Windsorizing using IQR gives us the lowest R square and the largest error on the test score. That makes total sense. So it's not good. It is the worst method, obviously. Which one is the best here? It seems to me that this is the best. The third one. The third one seems to be best here, and that is trimming using IQR. Or the second one, trimming using percentile. So trimming actually is better. Oh, actually, ignoring is better than trimming here. Ignoring is 63. So ignoring is also good, but definitely Windsorizing is not good. Windsorizing, both Windsorizing methods are the worst, right? Windsorizing are the worst. That's interesting. Based on R squared, this is the best. Windsorizing using percentile. But based on accuracy on the test set, Windsorizing is not that good. It's among the worst ones. Go ahead.
Regarding the
What's what?
Which one do I do for?
It depends on your goal. Is your goal predicting the future or explaining variation and interpreting the coefficients? Most of the time, prediction is more important. Therefore, we should stick to this mean of absolute errors. Most of the time, we should just refer to them. And in this case, the third method is the best, which has the lowest mean of absolute errors, 2.04. So there, that means trimming with IQR. Trimming using IQR is the best. And it has actually among the lowest R-squared values. Interesting. If both of them are important to you, R-squared and prediction, you should consider the top ones and just make a compromise. So, but we know that this is out. So fifth is out. And because it is bad in both cases. But we should select among these, the others. We see these two are good with respect to R squared. These two are good with respect to R squared. And these three are good with respect to R squared. So what do they share? They don't share this one. So one of these two. They don't share this one either because it's ignored. So this is the one that is good in almost good in both cases. The second method, trim using percentile. It's good here, the second best method, and this is the third best method here. So I would go with trim using percentile if both goals are important. Any question? Question? Okay. So we are good. Now, let's go to the next topic. Interactions. What is an interaction? Interaction is about a variable affecting the effect of another variable. This happens when the effect of another variable depends on the level of some other predictor has. Some other predictor moderates the effect of the other predictor. So the predictor moderates the effect of another predictor. For example, you want to sell ice creams, and when the sun is out, when it is a sunny day, you sell more ice creams. When it's hotter outside, when the temperature is higher, of course, also you sell more ice creams. So these two independent variables are significant, probably. But if both happens, if the sun is out and the temperature is high, it's a hot day, it's a hot sunny day, you sell a lot more ice creams because being sunny intensifies the effect of temperature. That's moderation and interaction. We're gonna have other examples. Is it the same as multicollinearity? The correlation between the two predictors? No. Multicollinearity is about the correlation between two or more predictors, right? But interaction is about the effect of one predictor on the effect of another predictor. The effect of one predictor on the coefficient for another predictor. So one predictor changes the coefficient for another predictor. Remember, so far we assumed that the coefficients are just constant. We estimate them and we just use them. But now we are considering some variation in the coefficients. The coefficients can be adjusted using predictors. Of course, we use constant values in the estimation, but the coefficient for one variable can change through interactions. Now, again, we are going to use the taxi data set, fare as a dependent variable, again. And the independent variables are tip and credit here. So we just ran the model, and actually we didn't run this model. It is a new model. It is different. We have two independent variables. So we can run the model. It's very straightforward. A multiple linear regression with two independent variables. So you already have taxi data set in your system in RStudio, hopefully. So you read taxi CSV, and then you make this linear model. This linear model. Fare as a function of tip and credit. Okay. The results should be like this. Just type this in your computer, LM of formula equals blah. You don't need to put formula equals. You can, but you don't have to. And run it and see if your results are similar to this. All the three coefficients are significant, including the intercept. Now we want to test if there is an interaction between the predictors. We create a new variable. We call it int, standing for interaction. Int equals tip times credit. And we use that like this. So we have this original model plus interaction effect. So fare as a function of tip, credit, and interaction. We add interaction as the third predictor. And we run the model. We see the summary. The summary is like this. 4 significant coefficients. All the coefficients are significant, including the intercept and the interaction. The interaction is the third predictor in this model. It's the third independent variable in this model. And all of them are significant. R squared increased slightly. It's 43.56. It was a little bit lower. It was actually 43.46. So 0.1% it increased. It's not much, but still the interaction is significant. How do we interpret the interaction? How do we interpret the coefficient for the interaction? The coefficient for the interaction is 1.67. See, 1.67. This is the coefficient for the interaction. How do we interpret it? We interpret it like this. When credit is 0, credit is a binary variable, by the way. That means the passenger paid with credit card. When credit is 0, the coefficient for tip is 1.65, right? When credit is 1, the passenger paid with credit card, the coefficient for tip is 1.65 plus 1.67, because we have two coefficients for tip. And the total coefficient for the tip would be $3.326. That means the effect of tip on fare is almost twice as much than we have credit when the customer uses credit, when the passenger uses credit. Okay, that's how you interpret the interaction. Let's go to R and see how we can run the code. I didn't have it. Okay, so we open taxi.csv and run the model without interaction. Without the interaction, R squared is 43.46, right? Now we make the interaction effect. I'm naming it tip by credit or tip times credit. Both of them would work. Instead of int, I think this is better to name it in a meaningful way. And we make a new variable. We run the model with the new variable included here. So we have 3 independent variables, and the result would be like this. R squared is slightly higher, 43.56. All the variables are significant. Great, right? Any question? So now you open packages.csv. You open packages.csv and remember the example that we had last week? Just try the variables, put the important variables that we had last week, and try the interactions between different variables and see if any of the interactions are significant. Okay, you just run the model with the interaction effect and see if it is significant or not. Go ahead.